So good morning everyone. So last day we have been discussing about eigenstates and eigenvalues. So we'll do a little bit more discussion on Hilbert space eigenstates and eigenvalues, but at a slightly later stage. And I think that you have all got the essence of eigenstates and eigenvalues. And there are two very nice sources that discuss eigenstates and eigenvalues and eigenvectors from a linear operation or matrix operation perspective. I'll put the links in the description box below, so feel free to check them out. And I think all of you should actually check this out to get the intuitive essence of eigenstates and eigenvalues. Okay, so today we'll start with the infinite square potential well. So a potential well is basically a region in space where the potential is 0 and outside that well or the potential energy is basically positive. Okay, so this is basically our potential well where the potential is basically 0 in some region in space. So potential is 0 means here the electron feels no repulsion, or here the potential energy of the electron is 0, and we are discussing about an infinite 1D potential well. So we'll be discussing an infinite 1D potential well. So let me write it down here. So as you can see, there are two terms. One is this infinite and another is this 1D. So infinite basically means that this potential is basically infinite outside this well. Okay. And 1D basically refers to this direction that this is a 1D structure, not a 3D structure. So, and the length of this 1D potential well, we will call it L, and we will take x equal to 0 from here and x equal to L here. So those of you who have already done semiconductor device modeling course, you are basically familiar with this infinite 1D potential well, because it was also covered in that course as well. So as we said earlier, that when we deal with Schrodinger's equation, what we generally mean is the time independent Schrodinger's equation, because the time dependence is fairly captured very well by this factor phi t is exponential minus I e by h t. So we do not worry about this factor because this factor is just an exponential of some phase. Okay, so generally we mean this time independent Schrodinger's equation, which is h cut square by 2m del 2 psi del x2 plus v psi equal to 0. Now here v is basically a constant inside the well, which is v equal to 0, and outside the well v is basically infinity. Okay, so we'll solve this Schrodinger's equation inside this well, and as it is obvious that no electron can exist outside this space inside the well, because outside this well the potential basically goes to infinity. Okay, so an electron cannot exist at an infinite potential. Okay, so we'll be solving the Schrodinger's equation for this potential well inside this well, that is. But before that, let us point out to some important information. The first important information is that, as we already know, mod of psi x square represents the probability density of finding the electron at position x. And since this is a probability density, we have the fact that integral of minus infinity to plus infinity mod of psi x square dx, which is equal to integral of minus infinity to plus infinity psi star x psi x dx, which is equal to 1. Okay, so this is first point. The second point is that the wave function psi x should be continuous in space. Okay, and d psi dx or del psi del x should be continuous in space except at places where the potential goes to plus infinity or minus infinity. So plus minus infinity. So plus minus infinity. Okay. So these are basically the three constraints, and based on these constraints we have to basically determine the various constants of the wave function, okay, or various parameters of the system. Okay, so let us go back to this infinite 1D potential well here. So I think I have made a mistake, so this should be actually psi x. So this is E psi basically, where E is the eigen energy of the system and psi is an eigen function or eigen state. Okay, so now inside the well we have V equal to 0, and outside the well V is equal to infinity. V equals to infinity, so psi x equal to 0. So the wave function is 0 outside this well. Okay, so psi x equal to 0 for x less than 0 and x greater than L. Okay, and inside the potential well this parameter V is equal to 0. So Schrodinger's equation inside this potential well basically becomes h bar square by 2m del 2 psi del x2 equals to E psi. And as we can understand that this equation can have this solution psi x equal to a cos x plus b sin x. Okay, because this sine and cosine are the only functions which return with a negative sign when we double differentiate them. Okay, not x, but we'll actually write it as kx plus b cos kx. We could have also written the solution in the form a e to the power I kx plus b e to the power minus I kx. So this is also another form of solution, but it doesn't matter whichever form you use. At the end, when you use the boundary condition, you basically get the same result. Okay, it doesn't matter. You may either write the solution in the form of this or you may write the solution in the form of this. So ultimately you have to gather or you have to calculate the different parameters of the system with the help of boundary conditions. Okay, so we will use the first form a cos kx plus b sin kx, and we have the solution in this form, but we have to determine the various constants or parameters of the system also. For example, this is one parameter and this k is one parameter, this b is another parameter. We have to calculate these parameters. Okay, so we'll be using the boundary conditions here. So as we know that psi should be continuous, so the wave function should be continuous, and since the wave function is actually 0 in this region, that is for x less than 0, the wave function should also be 0 at x equal to 0. So psi 0 is equal to 0. Okay, and if we put psi 0 equal to if we put x equal to 0 in this equation over here, what we will basically get is that this sine term is already 0 when x equal to 0. So this cos term is basically 1. So a is equal to 0. Okay, now we also know that psi x for x greater than L equal to 0, that is the wave function in this region should also be 0, because the potential is basically infinite, the potential is very large outside the wave, so the wave function needs to be 0. And since psi is continuous, so psi of L should also be 0. So psi x equal to L plus, which is basically slightly outside the boundary, this should be equal to psi x equal to L, because the wave function is continuous. And since this part is equal to 0, because the wave function cannot exist outside the well, therefore psi x equal to L should also be 0. Okay, so we put it in this form: a cos kl plus b sin kl equals to 0. Now we have earlier noted that a is equal to 0, so this term basically goes out of picture. So we just have b sin kl equal to 0. Now b cannot be equal to 0 because a is already 0. So if b is also 0, then the wave function becomes 0 everywhere, and 0 is basically not a wave function. So we should have, in that case, sin kl should be equal to 0, which basically means that kl is equal to n pi, and k is equal to n pi divided by L, where n is an integer and n is not equal to 0. If n is equal to 0, then the wave function should be 0 everywhere, so that is basically not a valid solution. Okay, that is a mathematical solution, but that is not a valid solution. Okay, so n is not equal to 0. Okay, now note that we have basically obtained k to be quantized, and k can only assume specific value. For example, it can only assume pi by L, 2 pi by L, 3 pi by L, 4 pi by L, etc. Okay, so these are basically the values of k which satisfy the Schrodinger's equation along with relevant physical boundary conditions. So as I have stated earlier, that in quantum mechanics, this quantization or some parameter only taking discrete values of parameters or discrete values of quantities actually come from the fact that we have to satisfy boundary condition. And as we have noted earlier, that for a free electron there was no boundary condition, so k could actually assume continuous values. But here there is a boundary condition that the wave function must become 0 at x equal to 0 and x equal to L. So k must be assuming some discrete or specific values, or there is a set of specific values among which k can assume one of the values. Okay, so k can only take specific values. Okay, k is not a continuous variable. So as we saw that this quantization or quantized nature or the nature of only taking discrete values come from boundary conditions in quantum mechanics. Okay, so we have this wave function psi x equals to b sin n pi by L x. Okay, now we still have to determine this constant b. Okay, so to determine this constant b, we take our first postulate, which is basically psi x represents the probability density, and hence the integral of mod of psi x square should be equal to 1 over space. Okay, and since the wave function only exists inside the well, we have integration from x equal to 0 to x equal to L mod of psi x square dx is equal to 1, which implies that integral b square sin square n pi by L x dx from minus infinity to plus infinity should be equal to 1. So we just express sin x in the form of cos x. So b square integral of minus infinity to plus infinity 1 minus cos 2n pi divided by L x dx. So we should have a half factor over here. So it should be b square by 2. Okay, so the relation is 2 sin square x equal to half 1 minus cos 2x. Okay, dx, this should be equal to 1. Now the integral of this part is basically 0. Okay, you can check it out, it's not difficult. So the integral of cos x is basically sin x, and if you put the boundary condition, sorry, we have done another mistake over here, so this should be from 0 to L. So if I put the boundary conditions from 0 to L, this part should be 0 basically. Okay, so let us do it here actually. So b square divided by 2, this integral of 1 is basically x. So x minus sin 2n pi by L x divided by 2n pi by L is equal to 1 from 0 to L. Now if I put 0 over here, this is already 0 because sin of 0 is 0. If I put L over here, then it becomes sin 2n pi, and sin 2n pi is basically 0. Okay, so this part basically becomes 0. So we have b square divided by 2L equals to 1. So b is basically equal to root over 2 by L. So the wave function, overall wave function psi x is equal to root over 2 by L sin n pi divided by L x. So this is the solution for the Schrodinger's equation inside our 1D potential well. Now your task is basically to calculate the average momentum and average energy for the eigenstates of the 1D potential well. Average momentum, average energy, and average position. Okay, so average momentum, average energy, and average position for the eigenstates of the 1D potential well. Calculate your answer keeping n as a variable. So which basically means that your answer should contain an expression which has n as a variable, so that if I plug in the value of n in that equation, then I will get the average momentum or average energy or average position for the nth eigenstates. Okay, n is precisely this value of n, k equal to n pi divided by L. So this value of n we are talking about in this case. Okay. Now we have already done this one-dimensional potential well, and as I said earlier that 1D potential well is not or does not account for too much of a practical case, but it is definitely useful for theoretical understanding that from where do this quantization of different parameters come from, or how to actually solve for wave function given the boundary condition. Okay, anyway. So we'll now go back to studying how we actually represent or how we actually write wave functions in quantum mechanics, or how we denote wave functions in quantum mechanics. So there are certain symbols, or there are certain conventions people have developed to avoid making expressions too clumsy. And although again everything is linear algebra in this case, including vector space, Hilbert space, etc. But I'll try to keep things as simple as possible because everyone here is probably engineering student. So I'll try to keep things very simple and only go through the basics so that you get the essence, but there is not too much stress on linear algebra. So first of all, as I said earlier, that the eigenstates of a Hamiltonian or eigenstates of any observable operator is actually such that the eigenvalues are real and the eigenstates are orthogonal and complete. Okay, so if we have a Hermitian operator, which is of course the case of all the observable operators in quantum mechanics, because if we measure value you cannot get complex numbers. If you measure for example momentum, you have to get a real value. If you measure energy, you have to get a real value. You cannot get a complex number when you measure the energy. So eigenvalues in these cases should be real. Okay, which means the operators in quantum mechanics are Hermitian operators. Okay, so we have Hermitian operators which gives us real eigenvalues, and the second thing is that it gives a complete orthogonal set of eigenstates. So orthogonal state means if psi1x and psi2x are two eigenstates of the Hamiltonian where psi1x is not equal to psi2x, then this integral over the considered space, let us say that I have boundary conditions over A and B. So integral over, we can actually extend it to infinity also, even if the wave function is 0, because it would not harm the mathematics. Okay, so integral from minus infinity to plus infinity, psi1 star x. Psi1 star x is the complex conjugate of the wave function psi1. Psi2x should be equal to integral psi 2 star x psi 1 x should, and this should be equal to 0. So this is basically the condition of orthogonality, and complete set basically means any valid wave function that satisfies the boundary condition can be broken down in terms of the eigen states of the system, can be completely broken down. Now let us say that I have a wave function, let us call it beta x as, and I am expressing beta x as the, or in terms of the sum of the eigenstates of the system. So C1 psi 1 x plus C2 psi 2 x plus C3 psi 3 x plus dot 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 dot. Okay, so beta x is a valid wave function of the system, and I am basically breaking down beta x in terms of the eigen functions of the system. Now how do we know this constant C1, C2, C3, etc. So it's fairly easy. So first of all, what we will do, we will basically normalize the eigenstates of the system. Okay, we'll use the eigenstates of the system as a basis, and so we'll normalize the eigenstates of the system. So we have orthonormal basis. So there is one additional condition when we go from orthogonal to orthonormal. So the first condition is this one. Okay, and the second condition is that we have integral of minus infinity to plus infinity psi I star x psi I x, which is equal to integral of minus infinity to plus infinity mod of psi I x square should be equal to 1. Okay, and how we have normalized this in the case of the 1D potential well is basically by this method. Okay, so we have normalized our eigenstate here. So this is the method of normalization basically. This is just an example that I want to give you to relate to the case that we have just solved for the 1D potential wave, that we choose the constant b such that the integral is basically 1. So that is how we normalize the eigenstates of the system. Okay, so again, so these two are the conditions for orthonormal set of eigenstates, and we call this orthonormal set of eigenstates as basis. Okay, orthonormal, the complete orthonormal, the complete orthonormal set of eigenstates of the Hamiltonian or any other observable operator is known as the basis. Okay, so I will just relate this with the normal 3D space that we often talk about shortly, but right now let us know these terms. Okay, this is known as the basis of the system. Of course, it is not necessary that we expand any wave function only in terms of the basis, but it is actually convenient because we can, in this case, easily determine the different constants C1, C2 and C3 of the system. So I repeat again that beta x is a wave function of the system that satisfies the boundary condition and that it satisfies the complete Schrodinger's equation, and beta x can basically be broken down in terms of the eigenstates of the system like this. Okay, because the eigenstates are basically a complete orthonormal set or orthogonal set. So it's actually fairly easy in this case to compute this constant C1, C2, C3. So let us say that I want to compute this constant C1. So what I do is I basically multiply this beta x by psi 1 star, and I integrate it from minus infinity to plus infinity dx, and this basically becomes C1 integral of minus infinity to plus infinity psi 1 star x psi 1 x dx plus integral from plus C2 integral of minus infinity to plus infinity psi 1 star x psi 2x dx plus all the terms up to infinity. Okay. Now note that due to orthogonality or orthonormality of the eigenstates, we will assume that the eigenstates here are orthonormal. So this term is basically 0. This we have already seen earlier, and all the terms that follows in this part is basically 0, because the eigenstates we have taken to be orthonormal, and this part of the term, this one is basically 1. Okay, not this part, but the entire integral actually. So the entire integral starting from here up to here, this part is basically 1, and here this part is basically 0. So we have this C1 over here. So C1 is equal to integral of minus infinity to plus infinity psi 1 star x beta x dx. So we can draw a similar conclusion on the general coefficient Ci, which is equal to minus infinity to plus infinity psi ix beta x dx. Okay, so we already use a similar technique in calculating the Fourier coefficient. So this technique should not be unknown to you, but I just thought of revising it a bit. Now, as I said that the eigenstates of a observable or of an operator corresponding to an observable quantity are basically real. Okay, eigenvalues are real and eigenstates are complete and orthonormal. Okay, so the simplest case we have solved is that of a 1D potential well, and let us quickly look at the case that if the eigenstates of the 1D potential well are basically orthonormal. So first is the orthogonality. So are they orthogonal? So we are considering the case of 1D potential well, and so let us consider any two uh, wave functions. So psi I is, let us say, root over 2 by L sine ni pi by Lx, and let us take psi j, which is basically root over 2 by L sine nj pi divided by Lx. So if these two states are orthogonal, then we will have this integral of minus infinity to plus infinity psi I star psi j dx is equal to 0. So we have to just check for this condition. So let us calculate this thing. So this becomes 2 by L integral from minus infinity to plus infinity sine of ni pi by Lx sine of ni pi nj pi by Lx dx, so equals to, so we have the multiplication of two sine, so this is equal to 2 by L into half integral of minus infinity to plus infinity cos of ni minus nj by L pi x dx minus, so we have a second bracket over here, integral of minus infinity to plus infinity cos of ni plus nj divided by L pi x dx. Now note that ni and nj are basically integers, so ni and nj are basically integers, so their addition and subtraction is also one integer. So we basically have 1 by L integral of minus infinity to plus infinity cos of na pi by L x dx minus infinity to plus infinity cos of nb pi by L x dx. So both these terms are basically 0. So we have 0 minus 0, which is equal to 0. Okay, so na and nb are basically integers over here, because this summation and subtraction of two integers are also integers. Okay, so we already have an orthogonal basis, and we have already normalized this this wave functions earlier by this factor 2 by L, and if you don't remember, you can go back and check how we have calculated this factor 2 by L here. So this set is basically an orthonormal set. Orthonormal set. Okay, so the solutions of the 1D potential wheel or the eigenstates of the Hamiltonian for the 1D potential wheel are basically orthonormal. Okay, so like this, any Hermitian operator or which basically is the operator corresponding to an observable quantity, they are basically orthonormal and complete. It is not possible to prove the completeness of this set here because that is complicated, but just take my word for it that the eigenstates of an observable operator are orthonormal and complete. Okay. And I again repeat that the reason why we take the orthonormal or orthogonal eigenstates of an operator to be the basis is because it is fairly easy to actually calculate this coefficient C1, C2, C3 if we basically express the wave function in terms of a basis. Okay, it is just the advantage that Fourier series actually gives us. Okay, we could have used any other basis, but there is no guarantee that that basis is orthonormal or orthogonal, and so we cannot actually compute in that case this coefficient C1, C2 by simple formulas like this. Okay, okay. So let us now move forward. So here I will describe how we generally express or how we write the wave functions in quantum mechanics. Okay. So here I draw an analogy between 3D space and Hilbert space so that you can understand it fairly easily in layman's terms. Hilbert space is again it's a quite complicated thing to actually explain it here, but just for your convenience or in very simple language, I can say that Hilbert space is basically a vector space. Okay, and we'll not go too much detail into Hilbert space because that again is too much deep into linear algebra, but we'll just say that it is a vector space just like our real 3D space is a vector space. Similarly, Hilbert space is a vector space with some basis vector. Okay, and wave functions basically live in the Hilbert space. Okay, so I hope you get satisfied with this much that it is just a vector space, just like our 3D space is a vector space. Similarly, we can actually, instead of 3D space, we can actually have momentum space. So Hilbert space is also a vector space like that. Okay, so in 3D space, we have these vectors I, j, and k. Okay, so these are the bases actually. So let me write it as basis. In Hilbert space, the things are the same because Hilbert space is also a vector space and 3D space is also a vector space. So there are a lot of similarities as far as the mathematics is concerned, but slight difference in the way how we basically treat them. Okay, so in Hilbert space, we have the basis as the orthonormal eigenstates of an observable operator. Now here, just like there is this interesting analogy that we can do is that this I dot I, so I'll put a hat here to denote that these are unit vector, which is equal to j dot j, which is equal to k dot k is equal to 0, and then I dot j is is equal to 1, and I dot j is equal to j dot k is equal to k dot I, these are equal to 0. So this, when we write it in Hilbert space or this wave function space, this becomes basically, this translates to integral of minus infinity to plus infinity psi I star x psi j x equals to delta ij, where delta ij is equal to 1 if I equal delta ij equal to 1 if I equal to j, and this is equal to 0 if I is not equal to j. So there is another similarity, that here we do the dot product and here we do this integral over here. Okay, so this is the second similarity. Now because of these two similarities, we can actually write wave function in terms of vector notations. So how do we write a vector s in 3D space? We basically write it as, let us say, a I cap or ax I cap plus ay j cap plus az k cap. So this is how we write a vector in normal 3D space. Similarly, when it comes to the vector space of wave functions, we basically write a vector, let us say beta x. So let me write it here, beta x as c1 psi 1x plus c2 psi 2x plus c3 psi 3x plus dot 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 dot. Now here in this case, in the real space, we have three basis vectors, or the basis vectors consists of a set of three vectors, which is the unit vector in the x direction, unit vector in the y direction, and unit vector in the k direction. But in the space of wave functions, the basis consists of all the eigenstates of the Hamiltonian, and as we have seen in the normal case, when we solve this eigenstates of the Hamiltonian for a 1D potential well, we get infinite number of eigenstates, because this n can take any value which is an integer. So n can be 10,000, n can be 15,000, n can be 1 lakh, n can be 1, 2, anything. So there are infinite number of eigenstates, and so the basis set in case of this wave function space consists of a set of infinite number of components, just like the Fourier space. Okay, when you write a Fourier series, there are infinite number of components which forms the basis of the space. Similarly, here also there are an infinite number of components that form the basis of the set. Okay, that forms the basis of the space. Okay, so how we generally represent this in terms of vector notation is basically, we can write it as s equal to, we just write it in vector form, ax ay az. Okay, and when we write s equal to ax ay az in vector notation, it would automatically mean that I am writing ax I cap plus ay j cap plus az k cap. So similarly, here also I can write this beta in wave function space as beta equal to c1 c2 c3 cn, just like that. Of course, it's an infinite space, but since we do not generally deal with infinite energy in the practical cases, we can actually truncate after a given basis set number. For example, when we express a wave function, when we express a signal in the terms of Fourier components, we can generally truncate the series, because the higher order components generally adds up little to the accuracy. So here also we can actually truncate our basis set to get reasonable accuracy, but let us not go into that. Let us just assume that we are dealing with an n component basis set. So we can actually express our basis, we can actually express our wave function like this, and this would automatically mean C1 psi 1x plus C2 psi 2x plus C3 psi 3x plus dot 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 Cn psi nx. Okay, now so I am just drawing the analogy between the two spaces. Now in this case we write this vector as beta like this. So this is known as the Ket notation, which was introduced by a famous scientist known as Dirac, and I hope all of you have heard the name of Dirac actually. And Dirac, unlike Albert Einstein, did not gain too much of an attention during his time, but he is actually a great scientist actually. I mean, of course he gained a lot of attention, but probably it was less than Albert Einstein, but I believe that he was no less than Albert Einstein actually. His contribution to this field and to the field of quantum field theory is actually enormous. Okay, so we just write, so this is just a notation which is known as the Ket notation, which was introduced by Dirac, and this basically means that when we write it, it means a wave function in the space. Okay, so let us deal with three components here, and so this would basically mean that C1 psi 1x plus C2 psi 2x plus C3 psi 3x. Now, how do we define the dot product of two vectors? So let us say that we are defining a dot product of two vectors, Si and Sj. So let me go to another page. So let us consider two vectors in real space. Si is equal to a xi I cap, not Si but Sm, let us say, which is equal to a xm I cap plus a ym j cap plus a zm k cap, and we have another vector, let us say Sn, which is a xn I cap plus a yn j cap plus this is a actually plus a zn k cap. So if I do the dot product of two vectors Sm dot Sn, so these are vectors, so I should probably put this bar over here. So this is just equal to a xm a xn plus a y m a yn plus a zm a zn. Okay. So similarly, let us now define two wave functions which are let us say beta beta mx. So let us say beta mx. So again, let me, before going further, let me denote this in matrix notation. So this basically can be represented by this row operator, row vector. Okay. So this is a xm a ym a zm multiplied by this column vector over here. So this is a xn a yn a zn. So we can do a similar thing for wave function space, given that the basis set is orthonormal. Okay, so let us assume that the basis set is orthonormal and we have two wave functions beta beta mx, which is c1m psi 1 x plus c2m psi 2x plus c3m psi 3x. So we are right now dealing with only three components of the basis vector. So and another wave function we have, which is beta 1n psi 1x plus 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 C2n psi 2x plus C3n psi 3x. So how do we define the inner product is basically let me just conclude another thing, that beta m and beta n can be represented in matrix notation like this. So beta m is equal so beta m is basically equal to C1m, C2m, C3m, and beta n is equal to C1n, C2n, C3n. Okay. Now, how do we define inner product in this space is basically so inner product between beta 1x and beta 2x is basically equal to integral of minus infinity to plus infinity beta 1 star x beta 2x dx. Okay. Now, what we get here is basically, because the basis is orthonormal, any integral of the form minus infinity to plus infinity psi ix star psi jx is equal to 0 for I not equal to j. Okay, and we can write it as delta ij actually. So in mathematical notation, delta ij, which basically means that this integral is basically 1 if I equal to j, and this integral is 0 if I is not equal to j. Okay, so this becomes, because of this orthonormality condition, this basically becomes equal to C1 C1m C1n integral of mod of psi 1 x square dx from minus infinity to plus infinity plus C2m C2n minus infinity to plus infinity mod of psi 2 x square dx plus C3m C3n minus infinity to plus infinity psi 3x square dx. Now this is also one which comes from this condition over here, that if I is equal to j, then this integral is basically 1. So this basically becomes equal to C1m C1n plus C2m C2n plus C3m C3n. And then in matrix notation we can again write it as C1m C1m C2m C3m, and then multiplied by a vector C1n C2n C3n. Okay, so if we use, as you can understand, that if we use a orthonormal basis set or orthonormal basis, orthonormal complete basis, then we actually need not take the pain to actually multiply all these things, do these integrals and things like that. It is actually enough to multiply these two coefficients together or do this kind of matrix multiplication together when we compute the inner product. So it actually becomes much easier to handle. Okay, now so just as I said that this inner product here is basically an integral of beta 1 star x beta 2x over space. So this is the inner product of two wave functions. Okay, now we have already noted that we write this beta 2 in the Ket notation, Bra-ket notation or Dirac's notation. We write beta like this, and beta is basically equal to, we can write it as beta 2 here. Beta 2 is equal to beta mn we have written earlier, so I will just replace it. So let me check the other page also. So here it should be mn actually instead of 1 and 2. Okay. Okay. So this is basically C. This is again in C 1n, C 2n, C 3n. Now, when we write this kind of inner product, it's actually convenient to have a representation of the row matrix as well, or the row vector as well. So this one is a column vector. So row vector would be something like A, B, C. Okay, this is some row vector actually. So we write this complex conjugate of this beta as the row vector. So and we just reverse this notation, we flip this ket notation. So ket notation is like this, and we write this vector inside like this to denote the complex conjugate and a row vector, which basically means the complex transpose actually of the row vector. We basically write it like this. So this is known as the bra. So this is basically ket, and this one becomes the bra. Okay, and this is basically our row vector C1m. Actually the coefficients can also be complex, so I would actually basically take the complex conjugate of the coefficients also. Okay, so similarly here also the coefficients can be complex, so I should have written it like this. Okay, so we are taking the, when we transform from this bra notation to this ket notation or vice versa, we are basically doing the complex transpose. Okay, we are writing the transpose matrix, and we are also taking the complex conjugate of the elements of the matrix. Okay, so then this integral, this inner product, which is basically the integral of from minus infinity to plus infinity beta mx beta nx dx is equal to c1 m star c1 n plus c2 m star c2 n plus c3 m star c3 m, which is again equal to, in matrix notation it can be written like this, just as I stated. And then in bracket notation, this is can be written as this. This should be beta over here. Okay, so basically this part is the bra, which is this part, and then again this part is the ket, which is basically this part over here. So we have written it in terms of Dirac notation or the bracket notation. Okay, so this is beta n. So this notation is again known as the Bra-ket notation, where this minus infinity to plus infinity beta 1 beta m star x beta n x dx in terms of the bracket notation can be written as beta m beta n, and in vector notation this bra notation basically becomes beta m, which is you do the transpose of the column vector and you take the complex conjugate of each element of the vector. Okay, so this becomes equal to C1 m star, C2 m star, C3 m star. So C1 m star is basically the complex conjugate of C1 m, C2 m star is the complex conjugate of C2 m, and C3 m star is the complex conjugate of C3 m. Okay, similarly, this ket beta n is basically C1 n, C2 n, C3 n. So this might take some time to get used to it. So do a little bit of reading on yourself, think about it a little bit, and you have to put some effort because this is something which is new probably for all of you. And so I'll see you in the next class. Till then, goodbye.